problem, we are given a graph of n nodes. So the nodes is starting from 0 to n minus 1. The graph is represented by a 0 index 2D array of graph. So this means from node 0 it can go to node 1 and node 2. So from 0 it can go to node 1 and node 2. Yeah. And let me just continue. So it is a 2D integer array graph where graph I is an array of nodes adjacent to node I, meaning that is from index 0, from node 0, it is connected to node 1 and 2. A node is a terminal node if there are no outgoing edges. So, for example, the node 6 or node 5, there's no outgoing edges. So that is called a terminal node. A node is a safe node if every possible path starting from that node leads to a terminal node. We have to understand this one. So what is a safe node? Every possible path starting from that node, with node, that node, leads to a terminal. That node means this node. So for example, we have a node 4. This node is called a safe node if every possible path starting from this node, so from this node 4, that is also this, So from this 4 leading to a terminal node. So this 4 is also a safe node because there's only one outgoing path and it leads to 5. So this 4 is also a safe node. So 4, 5, 6 is safe node. And let's just check node 2. Is 2 a safe node? So every possible path. So for node 2, how many outgoing edges? There's only one outgoing edges. So it means 2 is also a safe node. If 2 has another outgoing edges, definitely 2 is not a safe node. Let's check about the node 3. Let's check about maybe maybe it's just node 3. So for this node 3, it has a cycle. So for example, from 0 to 1, 1 to 3, 3 to 0. So but for node 3, it must lead to a terminal node. How it can lead to a terminal node? Like 3 to 0, 0 to 2, 2 to 5. It can lead to a terminal node for node 3. But this node, you can see every possible path. So for node 3, you can check the possible paths. So every possible path starting from that node. So this is a possible path. It goes to 0, goes to 1, goes to 2. It can go to 5, but it can also go to 0. So this is not every possible path. Every means all possible paths, but there's a path just like a cycle. But this drawing is really difficult to understand the problem. Let me make a drawing to easily understand the problem. Let me delete these areas. So for easily understand the problem, we need to know exactly what is the problem. So if we have a cycle like this, and inside the circle there will be a lot of nodes. I just make a drawing. So this is the direction. There's a lot of nodes. And there's also another node from here. It goes into the cycle. We are going to check which node is safe, which is not. Maybe here it is the outgoing node, like this. So if we are starting from this node, it goes inside and there's a cycle. So for this node, definitely it's not a safe node. Why? Because according to the terminal node, if there are no outgoing edges, so this is a terminal node. But for this one, there's no outgoing edges, so this is a terminal node. This is a safe node, right? But for this one, there is outgoing edges. But there is still a possibility that this one can become a safe node. All its paths must lead to a safe node. You can see it goes from here, goes here. It can lead to a safe node, but there's still other paths. It's starting from here. It becomes a cycle. So this is a not safe node. If the node inside the cycle, it is not safe. Because inside of the cycle, definitely it's not a safe node. and all the paths can't lead to this node. Yeah, because there's still other paths. For example, this one. It can go to here, but it can still go inside the cycle. So this means which node is safe, which is unsafe is clear. If the node is in cycle, and if the node is leading to a cycle, definitely this node is not a safe node. Yeah. If the node goes out of the cycle, and there's like this node, and there's no cycle for this node, definitely this is a safe node. If there's a cycle for this node, if there's another node, definitely this is not safe. Yeah. If we understand the problem like this, now for this problem I solved in topological sort before. So the topological sort, we just need to reverse all the edges. But for the topological sort, it's difficult to think about how to solve it. Normally you have to reverse the edges. Yeah, and then you're gonna use the topological sort. Basically, it's BFS to solve the problem. But this time I'm gonna use DFS to solve it. It means basically it's a cycle tracking. We need to detect a cycle, and from this cycle, yeah, we're gonna mark the color of the cycle, for example, as 1. So this means all the ones, it is unsafe. Yeah, if there's a safe node like this one, I'm gonna mark the color as 2, so this is a safe. So from beginning, all the color of the node will be 0. It means all the nodes has not been visited. Yeah, if I'm going for the DFS, so for example, starting from this node, I'm gonna set a color of 1, and then search 1, 1, 1. Yeah, until I find a color of 2. Yeah, so the DFS goes to here, goes to here. Yeah, but for this DFS, even it can detect a 2. So if it detects a 2, we will color it as 2. But if it is still going inside the cycle, we have to return. Otherwise, there's an infinite loop. So we have to return false. Return false for this node. Yeah. While we return false for this first node, so all other nodes, some of the nodes may be colored. So for example, inside the circle, we're gonna color it as 1. Yeah, maybe this has not been visited because it depended on the DFS, depended on the adjacency list we prepared, depended on this graph. Yeah, if it is going inside the cycle, we've already colored as 1. So for the next loop, if this one, yeah, if it is a 1, so we are sure it has already been colored, and we're gonna return false immediately. So this is why the time complexity is still O m plus n. M is the number of vertices, n is the number of edges. Yeah. So this means after the first visit of DFS, actually this node has already been visited. So for the next loop, it is just O one time for all other nodes. Yeah. Until we go to here, this node, we're gonna color it as 2 and get the result. Yeah, now let's get back to the code. So I'm gonna prepare the length of the graph. It means the number of nodes, and this color is really important for such problem. So this color is just a color array. So from beginning, all the nodes inside the color array would be 0. So this 0 means not visited. Yeah. So the color I set it as 0. Yeah. So this 0 color means all the nodes have not been visited. Now I will execute the DFS. Basically, this DFS is for the cycle tracking. If there's a cycle, definitely I will color it as 1. And if it is go inside the cycle, I still color it as 1. Yeah. If it is safe, if it is go outside and there's no cycle, I'm gonna color it as 2. Yes. So I will check the color I. If this color I more than 0, it means this color definitely has been visited. But I need to know if this color is inside of the cycle, it's still searching this color, or this color has already been visited. Yeah, already be a safe node. For example, like this 6 or 5, it is safe. But for this 0, 1, it's inside a cycle, it is unsafe. Yeah. I'm gonna return color I equal to 2. basically equal to 2, it means this is a safe. Yeah. Now I'm gonna start the coloring. So from the beginning, this means the color I definitely it is a 0, because if it is more than, I will have a return. So now if it is a 0, I'm gonna color it as 1. So this means I'm going to search this node. Yeah. If I were to search this node, definitely it's a DFS. So for Y in graph I'm going to search it. Yeah, I'm going to detect the cycle. So if not DFSY, yeah, so this if not DFSI means DFSY, it means DFSY is false. It means there's a cycle. Yeah, if I detected a cycle, what's gonna happen? Yeah, definitely I'm gonna return false. So this false just means this node I. If this node I is 0, it means this node is a false. I'm gonna return a false for this node. Yeah. Otherwise, I'm gonna color this node I as 2, and then I'm gonna return a true. Yeah, we have to use the 3 different colors for this kind of a problem. There's not so much coding, but it's really difficult to understand. What we need to return? We just need to return all the safe nodes. Yeah, so for I in range n if DFSI. Yeah, so this is gonna be the return. Yeah, let's check some node. For example, if this is node 6, yeah, what's gonna happen? We're gonna execute the DFS with node 6, because 6 is not connected to all other nodes. Yeah, so the color I currently color 6 is 0. Yeah, so we're gonna color it as 1. Do we need to execute the DFS? No, because there's no outgoing edges. Yeah, so this is the first condition. There's no outgoing edges for this. This is a terminal node. So this is a terminal node condition, and we're gonna color it as 2 directly, and we're gonna return a false. Yeah, so this is for node 6. So what about node 5? And what about node 4? Let's just start for node 4. Yeah, so what's gonna happen for this node 4? So for node 4, we put 4 inside. From beginning, it is 0. If it is more than 0, yeah, we're gonna return something, but we will color it as 1. This means we are going to search this node 4, and we're gonna search its neighbors 5. Yeah, if Y inside it, if not DFS 5, this DFS 5 is a true or false, and we have to we have to check it. So for the DFS 5, what are we gonna do? Yeah, we just go to here. This is the DFS 5. It is a 0 from beginning, and it's not more than 0. We will set this 5 to 1. Does this 5 have any neighbors? No, it has no neighbors. So I will color the 5 as 2. Yeah. So for the DFS of this node 4, I need the return from this node 5. Yeah, because for this node 5, I color it as a 2. It means for this DFS, it is a true. So similarly, for this DFS 4, I'm gonna still return a true. Before return true, I'm gonna color it as 2. Yeah, and similarly for all other nodes. If it is inside a cycle, we're gonna return false and color it as 1. Yeah, if it is safe, we're gonna return true. Before return true, we're gonna color it as 2. Yeah. So in this way, actually the time complexity becomes O(n plus n). It is not. Yeah, it is not n times m plus n. Actually, it is only m plus n, because after one DFS, for example, if there's a cycle inside or outside, we've already colored all the nodes. We don't need to color again. So this is why the time complexity is O(n plus n). Now let me run it to check if it works. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. As you can see, it's pretty fast and passed all the testing cases. And by the way, the color 1 is searching node. Yeah, it is still, this action is still going. It is still searching. We are not sure we're gonna return true or false, but we're gonna search it. If it is a 2, definitely, we're gonna name it a safe node. This is safe, already visited, and it is safe. Yeah. yeah, that's for this problem. Thank you for watching. See you next time.